so far we have discussed different things, right? So we have discussed the mechanical properties, and now we are going to see about the thermal properties. Okay. So sorry, thermal properties also finished, right? So today we are going to see the electrical properties, and yeah. So in thermal properties we have discussed the different parts, like how our melting point affects, right? So, and also we have discussed how the not only the melting point, how what do you call the phase transformation materials also. Okay, before that, I want to tell that there will be an extra session in after the session 11 and 12, right? We have 2 more sessions remaining, and after 12 we will have an extra session on Thursday. So maybe on it's on October, maybe Thursday. So you will receive that mail. There is no need to worry about that. Okay. So you will get that mail, and also next thing is if you have any doubts, you can just raise the question and ask. Right. I can answer. Okay. So okay then. Before moving into that, today we will discuss mostly about the electrical properties, and in last session I have also discussed the many of the electrical properties things, right? So in this lecture we will have electrical properties, and also we will discuss some magnetic properties. And in magnetic properties we will discuss in detail, because sir has rushed few things and he couldn't derive the magnetization formula, how you talk about the magnetization in terms of spins, right? So that part has been missed, and yeah, so we will discuss those things. And also, see, I have derived density of states in like initial lectures. Okay, so I guess there is no need, but still I will just give a brief recap on how to get the density of parts or the density of states, right? So no need to worry about that. Okay. And what else is remaining? So once you have the density of states, and then we will discuss the magnetization. In magnetization we will discuss how do you get the Curie point. Okay. And also in magnetization we will try to understand, like in class 12 we have discussed the magnetic moments in terms of integers. We didn't know that there can be rational numbers, right? Because we have only seen 4 mu b, 5 mu b, 5 Bohr magneton, 6 Bohr magneton. We didn't see like 2.4 Bohr magneton, right? So that thing will be explained in this lecture. So yeah, and also let's first, before going into that, let me derive the density of states, right? So that no, before going to density of states, let me derive the particle in one dimensional, the particle in 1D, right? Because I have rushed in last lecture because of insufficient time, so we will go through that again. Okay. And after that, yeah, okay then, let's move to the particle in one dimensional things, right? So whenever you talk about quantum confinement, so quantum confinement is nothing but, see, I have explained before how do I define the density of states, right? Now, before going into the potential well, one-dimensional potential well, let me clarify you why do we need the one-dimensional potential well. I mean, before going into this, why do we need to understand the one-dimensional potential well? Because you continuously hearing from past 3 to 4 lectures this quantum confinement. and why is this term getting so much importance, right? So for that you need to understand confinement. Confinement is nothing but you make sure nothing passes through after a certain dimension, right? So for example, if I fix my dimensions like this, so this is my x-axis and I fix it, so my particle cannot escape from these both sides, right? So I am confining anything in a certain space. So quantum confinement is not about the space, it's about the energy values, because see, the the psi function can be defined in terms of x comma t, and also you have spin for electron if I'm talking about. So, and t is its the frequency, it depends upon frequency, and x depends upon the momentum, right? So which is inversely proportional to k, and k depends upon momentum. So that means you are defining, so in real system you will see it as a space, but in reciprocal system you will indefinitely defining it as a momentum. So whenever you talk about momentum, there is an energy. I hope you people understand. Again, I will tell you again. So in real system we are confined in between 0 to L. This is the length. Okay, 0 to L I am confined. But how do I, what does that physically mean? So whenever you talk about something in real space, and whenever you apply some wave functions or do something, and you apply any types of operator, it will indirectly turn into the reciprocal space. And the reciprocal space of a real space is a momentum space. So real space, when it is converted into reciprocal space, it turns into momentum space. And what do I mean by momentum space? Momentum space is nothing but energy, because energy is directly proportional to p square, right? Kinetic energy is directly proportional to p square. So yeah, and that's about it. Now, why do we need to understand this quantum confinement? Again, so whenever I'm talking about nanomaterials, so we have defined different types of nanomaterials. For say, let's take an example of two-dimensional nanomaterials, because it has only one dimension in nanoscale. So if this is my thin sheet, and let's say these are in micrometer, tens of micrometers. Same goes for this guy, 100 micrometers. Let's say this is my 10 micrometer, and my thickness is 100 nanometers. Okay. So let's say my thickness is 100 nanometers, or I should say 0.1 micrometer, right? Because 1 micrometer will be equals to 10 to the power of 3 nanometers. Now I can say 0.1 micrometer. I can take this now. Now because the space is very low, now again, see, atoms are here also, atoms in the bulk, right? So there are atoms on above, below, and atoms are on bulk. So for example, we are talking about electrical properties. So what do I mean by electrical properties? Electrical properties mostly relate to the resistivity, mostly relate to conductivity. Now, we all know what is conductivity. Conductivity is nothing but how good a material can conduct an electricity. So higher will be the conductivity, better will be its conduction of electricity inside that material. So yeah, now now how do the conduction takes place, or the electrical transport or movement of current takes place via the motion of charge, right? So there is need for an electron transport, and atoms cannot move, they are fixed to their lattice points, but electrons can move, right, in solid. So my charge carriers are electrons, because these are the guys that are moving inside the material, which can freely move if you are talking about metal. Now, whenever I'm talking about the nanomaterial, as you have seen, the thickness is mostly 100 nanometers, 1.1 micrometer. So, in this direction, the electrons cannot move. See, right? From here to here, the electrons cannot move. In that direction, they cannot move. Right? And for such type of materials and for such type of scenarios, electrons should redistribute among themselves. Now, how does that happen? See, and this distribution comes from the potential. Right? So we are confining our electrons in the z direction. So that's how the quantum confinement came from. So now we know how we are. It's nothing but you are making the path small for electrons to move. So they cannot move in z direction because it is only of 100 nanometers. Right? Then what happens? So you have successfully confined your electrons in a z direction. Okay, we understood that. Now, what exactly happens? So what are the scenario because of that? Right? What are the effects because of this confining? Now, the results are, so whenever I try to confine something in one dimension, so let's say, now we will talk about the one-dimensional potential well. See, suppose I have an electron here. Suppose I have an electron here, and it has, it is inside a potential well, because every atom, see, for example, I can show you, these are my nucleus, right, which has protons, so there is a positive charge, and they will create a field, positive field, see, I am still explaining classical thing because for you to understand, right, because this potential is purely quantum mechanical, but for understanding we can just relate it to the physical physical terms. Okay, so around every nucleus there is a potential, and because the atoms are very close, you have a continuous potential everywhere, and this potential is given as V of x, the potential energy. Okay, so if I write as potential equation for my electron inside my not inside these atoms, because it will contain so big equation. So for simplicity, we can consider our electron is inside a potential well, and besides this, our potential is infinite. Same, beyond this wall, the electron cannot go, right? So for example, even if you can see, whenever you have a material contains atoms and atoms contains electrons. So you don't see the electrons coming out of that material. If you put an iron block outside, and you don't see electrons coming out of the iron block. Why? Because they are bound to that potential. Right? They cannot come out from that. So the same thing we are simply the same thing we are doing here. Let's say this is my iron block, this guy. Just for assumptions, okay? It has 0 to length L, is the total length. Now, it is inside a potential, and beyond these walls, wall 1, wall 2, this electron cannot flow out, right? Because it is bound to that. Now, if I try to write a Schrodinger equation, and we all know the Schrodinger equation, right? So it's simple, which is h square by 2m or d square psi of x. Let's say our wave function is time independent. Okay, it doesn't depend upon what we call time. Okay, it is independent, totally independent of time. Dx square plus this is the kinetic energy part, okay, and this one is the potential energy part, equals to total energy. It's as simple as that. So this is nothing but the energy operator, total energy operator. Total energy operator consists of kinetic energy plus potential energy. We have all read these things in class 12, so there is no need to explain why we consider total energy as kinetic energy plus potential energy. You can consider even other energies also, but because we are only considering the single electron, so there is no need for consideration of vibrational, all these things. Okay. So in terms of phonons, we have taken the vibrational energy, right? So yeah. Now, see, let's even consider another assumption is our potential energy well is 0 from 0 to L. And what about these guys? So let's define this. Okay, it is 0 and it is infinite, or you can say infinite when x is, so let's write it, x is okay, and it is infinite and x is less than or equals to 0. Okay, and again infinite, x is less than equals to. Okay, so these are our assumptions. So what else we do have now? So this guy will go out because we have traded it as 0. Now our total energy will be equals to the only kinetic energy part. H cut square by 2m d square psi of x dx square equals to total energy term. Okay. Now, so how does it look like? It looks like this guy. See, if I write it like this, so d square or you can consider d square minus 1 related. It is closely related to that, or d square minus kx, constant kx. Okay, so it is related to that. Then what is my solutions for this differential equation? The solutions are psi equals to a e power I kx. Okay, and what is my k? K is my constant, right? How do I get that? It is simple. So if I just put everything on this side, then e 2m, instead of that I will write it again here. So just write the whole equation. Okay, so for write only d square psi of x is equals to minus e 2me upon h cut square times psi of x. Okay, so yeah, so far so good. So even I can consider this term as k square. So d square psi of x minus k square psi of x, which is equals to 0. So d square minus k square equals to 0. Then I have d plus k and d minus k. So for that you will you will directly have a solution which is directly solved. Okay, you do not need to think too much here. These are direct differential equation solvers. Okay, so this will be a e power I kx. That's it. Right, now again for this the general solution should be like this. Okay, so it should be b e power minus I kx. See, because if I have d plus k, then I should get this guy. If I have d minus k, then I should get this guy. Right? Now a and b are my constants, so this can be again written as, so we all know what is e power I kx, which is cos kx plus I sin kx plus b cos kx minus I sin kx. Okay, so please, you can do it yourself also. All you have to do is just take h cut square by 2m to that side. This will become 2m e by h cut square. So all you have to do is just assume a constant times square, because that will be very easy to solve the differential equation. So it will finally turn out to be like this. See, so why I wrote d square, see, this is the final turning. So d square psi of x minus, d square is nothing but double differentiation. Okay, so minus k square is nothing but 2m e by h cut square, and psi of x comes out. So psi of x cannot be 0, then d square minus k square should be 0. So it can be written as d plus k and d minus k. And if you solve the d plus k, you will have a general solution of this, and if you have d minus k, then you will have a general solution of this. Okay, the general differential equation solution. Okay, so if I write, and we know e power I kx can be written in terms of cos kx plus I sin kx. So if I take out only cos terms, so it will be a plus b cos kx plus what's the remaining term? So a cos a plus b. Okay, so the final will be a minus b times I sin kx. This can be written as another constant, which is c cos kx plus d sin kx, where c is my real number, d is my imaginary number. Okay, so now we have a general solution, and whenever you have a general solution, then the next step is to apply boundary conditions. Apply boundary conditions. Right. Now when you apply boundary, now what are the boundary conditions? We have defined our boundary conditions, right? See, now we all know what does the wave function gives. Wave function will talks about the probability. Mostly it talks about the probability. Okay. If you are talking in terms of x, then it tells you about what is the probability of finding an electron at the position x. And if you are talking about the probability of, if you are talking about psi of k, then we will tell what is the probability of electron having that energy k. Okay, so yeah, so psi of x is mostly about the probability, right? And to get the probability, you just have to multiply psi of x with its complex number, conjugate term. Okay? Because psi of x is a complex number, and you multiply it with the conjugate complex, then you will get a real value. I hope everyone knows this, right? So if I have a complex number, and if I multiply or do a dot product with the complex conjugate number of the same number, then it will turn out to be a square plus b square. Let's say if this is my function, then it will turn out to be root of a square plus b square. I hope everyone knows this, because you people have studied this thing in complex numbers, right? Now, Let's do the boundary conditions. Yeah. So v of x, the potential will be 0 if for v of x is 0 where for x equals to 0. Let's say if I am at x equals to 0, at x is tending to 0, then my v of x is 0. Okay. Let's first solve that. My x equals to 0, or instead of that we can write what is my wave function at x equals to 0. My wave function at x equals to 0 is 0. Why? Because my potential energy is infinite. If my potential energy is infinite, I cannot find my electron there because it is not allowed. See, if you want to go into potential energy well of infinite, then you must have energy of infinite, right? And we all know the electrons cannot have energy of infinite value, right? So that's why we are not allowing that electron to move to the next beyond that wall. So that's why our wave function, that means the probability of finding the electron is 0 there. Then that means the psi of x is also 0. If psi of x square is 0, then these two must be 0, or one of it should be 0. If one is 0, then the other should also be 0. Right? So you know the relation, right? If A times B is equals to C, and if C is 0, either A or B is 0, and we know the B is complex conjugate of A, then if B is 0, then A is also 0. So that's why our psi of x is 0. And at x equals 0, psi of x is 0. And we know what is my psi of x? Psi of x is 0 at x equals to 0. So C cos k of 0 plus D sin k of 0. So this guy goes to 0 and this guy goes to 1. So C equals to 0. Then what is my wave function? Then my wave function is psi of x will be equals to sin d sin kx. Right, and also if I try to do at x equals to L the same. See, even at x equals to L, my v of x is infinite. So I'll add one more time. So at x equals to L, and we know at x equals to L, v is infinite. Then again, the psi of x is 0. If my psi of x equals to 0 at x equals to L, so psi of L equals to d sin k L, that is 0, right? And this guy cannot be 0, right? Constant cannot be 0. If the constant is 0, then the whole psi of x is 0, whatever you put, right? So that's why only assumption can be sin k L equals to 0. And sine can only be 0 when it is a integral multiple of pi. So, integral multiple of pi, right? Then my k will be equals to n pi by L. This is one relation. This is relation number 1. Okay. Then if I put my values here, then psi of x will be equals to d sin, what is my k? N pi x by m. And where n equals to 1, 2, 3, it is an integer. Now, The next thing is, how do I define D? How do I get D? Right, that is also one thing. You need to know what is the constant. So psi of x, again the normalization. What do you mean by normalization? Normalization is nothing but what is the probability? The probability always lies between 0 to 1. Okay, now moving back to how do, so our problem is we have defined everything. Now we do not know what is my value D. Now how do I know D? That can be defined from normalization. Now what happens in normalization? Again, what is normalization? Right? So whenever I'm talking about probability, right? So we all know what is the probability of all the events, right? So for example, if I'm talking about coin, heads, tails. So what is the if I'm talking about one coin, what is the probability of head? Half. Probability of tail? Half. What is the probability of total events? P of h plus P of t. Half plus half is equals to 1. So normalization is nothing but you add every event that's been happening and your final value should be 1, because probability cannot be greater than 1, right? It doesn't make any sense, right? So when you add all the probability events, all the events probability, it should be equal to 1. So the same goes here. This is my potential energy well. Let's say my probability of finding my electron here is 10%. Okay, what about here? It should be maybe 20%, and here it may be 30%. Here it may be 50, or not 50, exceeds 100, right? So it may be 15, and here it may be 25, so 60 and 3, right? Yeah. So when I add all these probabilities, it should be equal to 1, right? Now that's why the probability from 0 to L, and it should be the normalization, the normalized value, because psi of x doesn't have a significant meaning, right? So wave functions do not have significant meaning, and when you do the what do you call the normalization, they have significance meaning, right? When you talk in terms of probability, and to get the probability, you have to multiply your wave function with the complex conjugate wave function of the same wave function. Then you will get a real value. That real value tells you that real wave has a significance meaning. Only the wave function doesn't have significant meaning. Please remember that. So square will be equals to 1, right? Now if I do that, so psi of x is, and d is my what? Because we are talking about sine term. Sine term, d is my imaginary number. Please remember that. Your wave function should be a complex number. If your wave function is not a complex number, it will not make sense, right? So now, so d square, let's say d is my sum a plus ib, then d complex conjugate will be a minus ib. So d will be d square sine square, what do we have, n pi l upon, x upon l, and we are doing it from 0 to l, use dx, right? Dx. Okay. Okay. we know the this relation, trigonometric relation, cos 2 theta will be equals to 2 cos square theta minus 1. Then 2 cos square theta is, so 1 minus sin square theta minus 1. 2 minus 2 sin square theta minus 1, which is 1 minus 2 sin square theta. So sin square theta will be equals to cos 2 theta minus 1 upon 2. And we cannot directly integrate sin square theta, right? Because there is no such function of integrating sin n power x. There is a relation. If you derive it, you will get. But for simplicity now, we will not go through that. So we will just use a simple correlation this. Then this is 1, 0 to L. I have the square value here because it is a constant value, right? It doesn't depend upon x. So cos 2. Let's take x equals to, not x, by x by L, right? So let's take n pi by L as b, okay, small b. To avoid writing too many times n pi by L, okay, 2bx minus 1 upon 2. So d square, if I take things common, 2bx by 2 minus 0 to L, 0 to L, half. Everything comes in dx. So what is cos 2 theta? I hope, oh, I made a mistake, my bad. It is not cos 2 theta minus 1. It is 1 minus cos 2 theta. My bad. 1 minus cos 2 half. So half, let's take half outside because it is a constant. Half dx minus 0 to L, again half common, cos 2b x dx. And we know integral of cos x, integral of sin x is minus cos x. And if it is integral of cos x, then it is sin x, right? So hope I am right. Let me check it. What is the integral of cos x? Okay, integral of cos x. Yeah, it is sin x. Good. So I have d square, which is 1 here, and you will have L by 2 minus, it is simple, and I guess I don't need to write it again. Anyway, I will write it. Okay, so half, so integral of constant is x, right? Then it is x, limit from L to 0 minus half cos 2, integral of cos constant x will be sin constant x by constant. Okay, so sin 2bx upon 2b, which is equals to times 0 to L. Okay, so 1 equals to d square L by 2, because it will become 0 for one part, minus half First, let's put sine L. Okay. So sine. What is now 2b? Let's write what is my 2b. Okay. 2b is nothing but 2n pi upon L. So the second the first limit and the final limit, right? The initial and final limit. So my final limit is this guy upon 2n pi by L minus sine. Now the final limit, the initial limit is 2n pi by L times 0 upon 2n pi by L. And you know sine 0 is 0, L is cancelled, and we all know sine n pi is equals to minus 1 whole to the power of n. Okay. And if sine 2n pi, then whatever the value of n, it is 0 to the power of n. Okay, whatever you put values there, even you put 1 integer anything, it will be a 0. So this guy is also 0. Then what are we remaining with? We are remained with d square L by 2, and d equals to root of 2 by L. Okay. Now if I try to substitute my final equation, psi of x will be equals to root 2 by L sine n pi x. This is our wave equation for an electron inside a one-dimensional infinite potential well. People call it like that. Okay. Now this is a term of n because it depends upon n also. So if I tell you if my n is 1, then it will be 2 by L sine pi x upon L. So x is ranging from 0 to L. So this is my potential well, and for n equals to 0, I am writing for n equals to 0, and at x equals to 0, psi 1 of x will be 0, so it starts from here, and at x equals to L, it is again sine pi. Right? Oh, I guess I have made a mistake here. Sine 0, 0, right? So if I'm talking about sine 0, then it should be 0. And sine 360 is again 0. Yeah, it is 0. Oh, it is n pi by 2. Okay. I guess I have made a mistake. It is n pi by 2, then it is minus 1 to the power of n. Okay. So yeah, it should be like this, and n should be a odd number. Then only I will write as sin n pi by 2 equals to minus 1 to the whole power n. Even sin n pi will be 0. There is no need to measure only to n pi. And at x equals to L, it will be sin pi. Again sin 180, psi of x will be 0. So again it is ending at 0. What happens in between? So if I take x equals to L by 2, then sin pi L by 2 upon L gets cancelled, sin pi by 2 will be 1. So it is reaching highest point at pi by 2. Then again this function will decrease. It will increase from here to here. It will decrease from here to here. That is what we see in sine functions. Right. So this is for psi 1 of x. Now what about sine 2 of x? Right, then my function will be root 2 by L sine 2 pi xy. Again, if I substitute sine from x equals 0 to L, it will have 3 zeros. So it will increase from here to here, decrease from here. And if I do it for sine 3 of x, then again we will have another standing wave. It will be like this. And this will go on. Now, how do I write energy? Right, so how do I write energy? Energy is written as h squared square k square upon 2m, because we know P equals to h squared k. Momentum space can be written in terms of k space, because k space and momentum space are related, right? And we know what is my k, so if I write it here, it should be h squared square. It is n square h square upon 8m. So these are my energy values. And this guy will tell you the energy levels of electrons. If I tell you 1, then it is. If I say it is 2, because the energy is increasing, and the difference is right. So that means the energy is evenly spaced. So that these are the energy levels this electron can take, and it cannot take in between, like half. No, these are not allowed, and we call these levels are allowable energy levels. And in between we have formidable energy levels. So there the electron cannot take that energy. Okay, so now you understand whenever you confine something. So we were discussing this problem, right? What happens if you confine something in a little space? If you confine something in a little space, then the energy values will get brought up. It will not have a continuous energy value. So it means it cannot take any energy value, right? So if you make some confinement in nanometer scale, then the particle will take only certain amount of energy levels. Okay, it cannot have like different any type of energy. Okay, it can only get few integral multiple of energy levels. Okay. So that. Now let's move on to. So this is about the particle in one-dimensional box. Now coming to the density of states. Now see, if I do not confine, then what happens? I have explained this before. Every atom has some atomic orbitals. Right, when these atomic orbitals come close together, and they come close together, like these atoms comes close together, then these atomic orbitals will overlap and will give degenerate states. We all know that because this is what happens in hybridization. When you form bond, there will be degenerate state. Degenerate states is nothing but so for example, 4 orbitals of different energies will come and overlap, and they will give again the 4 orbitals but with same energies. That is what we call as degenerate states. Okay, so they have same energy levels. So that is what we call. Now when I have an atom, just like I have said before, it has an electron, so electron will have some certain energy levels, and if I have another atom, it also has some certain energy levels. Okay, when these two get close together, so when these two atoms are combined, these orbitals will come close together, right? So electrons can take this guy and this energy level also, and if I even get another atom, then again another orbital will come into picture. So instead of writing like this, so you will understand. Okay? So let's say this is my atom. It has my atomic orbitals. Okay, it has energy levels like this, and then I put another atom. So if I have another atom, then again my energy, these are the atomic orbitals. Okay. And if I get another atom into the bonding, that orbital like this. And if I get even another atom, and it will also have some orbitals. So like this. So if I get n number of atoms, okay, then these atomic orbitals will be filled. Same goes for this guy also. Okay, and most of the energy of the electrons will be at minimum level, right? So no atom, again I have said before, no system in universe will try to have a high energy state, right? Because it tends to have a low energy state, so that's why the electrons will also try to have a low energy values. So that's why they mostly will fall under this guy, the low energy guy. So these are energies. So this is the low energy term. And whenever these orbitals will come close together, they will form a continuous energy strip, and we call this strip as a band. Okay, and you have two different types of bands, and one is the valence band, where the most of the electrons will try to lie if you do not supply any type of energy, and if you give some type of energy, the electron will hop from this band to this band. Okay, and this theory is called molecular orbital theory. So you can just study in any lectures, like in physics, in like solid state physics, you can study this thing. Okay, so the electron will hop from one band to another band, and the band which is free of electrons, and that band is called as conduction band. It is a high energy band. So when electrons will jump from valence band to conduction band, they start conducting. And what do we mean by conducting? Conducting is nothing but because they're free. They're free, right? They cannot move freely there, because here every atomic, whatever the atoms were there, and all the electrons are located here. So for example, if there is a room and the door is on left side and another door is on right side, now you have to move from left to right. You can only go through this. So for you to move, if my room is crowded, can you move fast? No. If my room is too crowded, you cannot even enter, right? And same goes for if my electrons are crowded here, they cannot move freely. And if my room is totally empty, then electrons can move freely from here to here. And same happens in conduction band. And because the conduction band is very, like, totally, not, I shouldn't say totally, but it is free, right? Free of space. Okay. So electrons can just hop onto this band and they can continue to move. And based upon this, we have defined metals, semiconductors, not metals. I did the same mistake in last lecture also. It is conductors, semiconductors, and insulators. If my band gap is very small, then I say these are conductors. And if my band gap is 1 to 4 electron volts, where silicon has 2 or 3, I do not know the exact number. So 2 electron volts, I guess let's take for example some element has 2 electron volts, then we call it as semiconductors. And if my band gap is too large, then we call it as insulators. Few tens of electron volts, then we call them as insulators. In conductors, mostly you will find metals like iron, copper, zinc. You don't even need to give them energy. They will just silver. They will just conduct electricity. Why? Because the conduction band and valence band are even overlapping. Leave about the gap. We are not even talking about the gap. Some metals have the conduction and valence band overlapping. Right? There is no gap at all. There is no need to supply energy. They will you just supply current and they will do the thing of moving the charge. Okay, so those are called conductors, and there are something called semiconductors. Semiconductors mostly the silicon, the carbon family. It contains silicon, germanium. Okay, and also with boron, nitrogen family, people are trying to make a conductor. We have different semiconductors, right? Not only silicon, germanium semiconductors. We even have gallium arsenide one, which is highly effective. Okay, in some cases when compared to conventional semiconductors like silicon wafer. So it's simple. How do you differentiate between metals and semiconductors? How do you differentiate? One simple way is you just find out the resistivity. Okay, you just find the resistance. Okay, so in metals or in conductors, I should stop writing metals for conductors. So in conductors, the resistance will decrease with temperature, because when you increase the temperature, the electrons will scatter more and they will have collisions more, so that because of that the resistance will increase, the conductivity will decrease. In semiconductors, the conductivity decreases, right? So in metals, when you increase the temperature, the electron will scatter more and they will collide more, and because of that the resistance will increase. That means the conductivity will decrease, right? So my resistance will increase. But if I'm talking about semiconductors, the resistance will decrease up to a certain temperature. Why? Because whenever I'm trying to increase the temperature, I'm trying to give energy to the system. When I'm trying to give energy to the system, the electron will gain energy and they will jump from valence band to conduction band, and they will start conducting. So that's why my resistance will decrease. Okay, so this is the basic relation between the conductors and semiconductors. Okay, you don't need to like find out insulators, because you can just say that there is no current direct even after increasing temperature. Simple. Okay. So this is about that. Now I hope. Do I need to derive the density of states again? Right. Should I again derive the density of states? I'll give just few hints. I will not derive for everything, okay? I will just derive for 3 dimensions, which is the most difficult one. Okay. Okay. Now, as I have said before, whenever I'm talking about the real space, what is the mathematical correlation? So far we have defined real space and reciprocal space, right? So how do I define my reciprocal space mathematically? So if my real space is this and my reciprocal space is this, then how do I define it? So if I do the Fourier transform of my real function, then I will get the reciprocal space. So mathematically, Fourier transform will tell you what is the reciprocal space that you are getting. If I do it for time, then I will get the frequency. If I do it for real space, like length, dimension, then I will get the energy or momentum, which is nothing but k space. And because we are only discussing about the real space, so x, y, z, okay. So as I have defined before, psi of x will be equals to root of 2 by L sine n pi x. If I do the Fourier transform of this guy, then I will get the momentum operator. That is what I mean. And this will give out. So whenever I do the Fourier transform of psi of x, then this psi of x will omit my k value. And what is my k value? My k value is nothing but the momentum. Okay, I can do it, but it will take time, so I will not perform it. It is rather simple, you know. All you have to do is just e power minus ikx times psi of x. What is my psi of x? Sin n pi x by L. And what is my sin n pi x by L? I can write my sin n pi x by L as e power ikx minus e power minus ikx upon 2 sin kx, or 2i. Right. So all I have to do is just then integral 0 to L. I will not derive the whole thing, okay? So it will take time. So I will just write everything. So after that, it is just simple mathematical equation, okay? So let's say e power minus ikx times e power ikx minus e power minus ikx. Okay? So I hope I'm writing right. So sin kx is this thing, right? E power ikx is cos kx plus, yeah, it is right. e power ik minus ikx times e power ikx will be 1. So at one point I have this guy, dx minus 1 by 2 I e power minus ikx whole square dx. Okay, so then it is simple. From here it is simple, right? So I have by 2I and then by 2I equal so it will turn out to be what is my kx, right? So momentum, if I put out everything, then e equals to kx. So what I have is k. So finally I will remain with the momentum operator. Okay, all you have to do is integration from 0 to m and you will get the value. And what you will get a relation in terms of k. And what is my k? K tells you about the momentum. Right, you know P is equal to h cut k. Right, so you will get a relation like this. It will omit, whenever you do the Fourier transform, it will omit you the momentum part. So that's why whenever you try to do the Fourier transform real space, you will inherently turn into a reciprocal space of momentum space. So for example, if I define x, y, z as, let's say, x, y, this is x, this is y, this is z. Okay, so 1, 2, same the graph itself. And if I do the Fourier transform, this will turn into reciprocal space. This will be kx, this will be ky, this will be kz, this will be k1x, this will be k1y, this will be k1z. Right, then if I want to know what are my density of states. Density of states is nothing but the number of states per unit volume. What is density? Density is nothing but mass by volume. The same goes to the number of states per unit volume in a given energy gap or in a given energy interval. That is what we call as density of states. Okay, so G of E times dE from 0 to will give you density of states. That's all. There is nothing big calculation there. So now how do I define these guys? Because I know the relation in K, so I can just write in terms of K. Dk. Because it can be directly converted. Okay. Because E equals to h cut square K square upon 2m. It's just a conversion. There is no need to apply high level of math there. Right? It's a simple one. And if I'm talking about 3 dimensions, then it will be a sphere. But density of states will all lie inside a sphere. Okay. Then my k will be equals to kx square plus ky square plus k square. Then my g of k will be equals to dk will be equals to 4 pi square or 4 pi 9 4 pi k square dk upon 2 pi by L whole cube, right? And I know E equals to x cut square k square upon 2m. And what is my, if I do the differentiation, k will be equals to 2m by x cut square dE, and dk will be equals to 1 by k m x cut square dE. So dk will be equals to, if I write everything in terms of E, then 2m by x cut square over a half e power minus 1 by 2. So finally my relation will be G of E some constant times E power half. So that's why my depth substrates will look like this, a parabola. That's it. And if I'm talking about sphere, then it will be 4 pi square k square. If I'm talking in 2 dimensions, then it will be what? It will be perimeter, then it will be 2 pi k dk for 2 dimensions. And for 1 dimension, it is just integral of dk. Right? So that's all about density of threads. Okay. So you can refer to the last few, the initial lectures where I have defined these relations. So it will be time waste to define again and again these things. Now, moving on to the most important and interesting topic is magnetism. Here's the magnetic properties. Okay, when I talk about magnetic properties, there is a big confusion between B, H, and magnetic flux density, magnetic intensity, magnetization. Everyone is clear about magnetization. It comes from the system. It comes from the system. And H is a magnetic intensity, that means that we are applying it. Or you can call it as an external force. Okay? And magnetic flux density is a combined effect of these two. And we can just replace B to H. It depends upon how you are defining the system. Okay. So when you are talking about spins, we just replace H by B. Right. So I hope I am clear, because these two are most confusing. When to use, where to use is very confusing part, right? So, and if my M is not interacting with my H, then B is nothing but H. Okay, you can just replace B with H. You can, in one case, if my M is not interacting with H, okay, with my external field, then you can replace B with H. That is one case. And even when you're talking about the magnetic moments, you do not use H, we use B. Okay, so and the magnetic moments come from the spins and the orbital magnetic. Then we will go quantum mechanically. Okay. So Faraday's law says that if we have a current carrying loop, then there is a creation of magnetic field. And if my electron, so current carrying loop is nothing but the electrons moving. So for example, if my electron is moving inside a circuit, and this can be treated as a current carrying loop because the motion of electrons, the motion of charge is nothing but current. Then I can represent current as minus IQ by T. Q is nothing but my I minus is written because my charge is negative. Okay. And what is the time taken for a complete circuit? The distance by speed will give you time. So what is the distance traveled? Nothing but the circumference or the perimeter, and perimeter of a circle is 2 pi r, and that is the total distance. That is the velocity of electron or speed of electron. Then if I substitute, is minus q by 2 pi r times v. Okay. Now, what is the magnetic moment? Magnetic moment will be given as current times area of the circuit, area of the loop. Okay, then minus q by 2 pi r v minus pi r get cancelled, pi get cancelled. Then remain with minus, let's write charge, okay, 2 r times v, and we all know what is r cross v, L r cross v, okay. That is angular momentum. What is angular momentum? Angular momentum is nothing but linear momentum cross r, the distance, cross product. Okay. So what is my momentum? Momentum equals to mv. If v can be written as momentum by m, then this will turn out to be magnetic moment, and written as minus e by 2m times the angular momentum. What is my m? M is my mass of electron. So this is coming from what? The electron revolving around the nucleus. And that's why we call it as orbital angular momentum. This guy. Okay, so and there is also the spin. Spin of electron around itself. And that is called as intrinsic spin. See, the electron is rotating about itself. There is also this intrinsic spin that is given as S, and this S is given by spin magnetic moment. So my final total magnetic moment will be minus E upon 2m L plus minus E upon m times constant G, and I have S. What is my G here? G is, you can say, landed G factor. So it is a proportionality constant. Okay. So if people have tried, people have found the value by calculating the total magnetic moment of electrons. So it will come close to 2.02 something. Okay. People who are as a landed G factor. Okay. It can be. This is derived in. If you want to know the exact value, then you can just refer to yeah, this is derived in quantum electrodynamics. Okay, again, it is out of the scope of this lecture. Okay, there is no need to go deep into it. So if you have any interest in finding the value, so you just refer to the lectures on electrodynamics, quantum electrodynamics. Okay, so there you will find how to find this value. Okay, so right now, see, before going into that, the magnetism, you know where it is coming from. It is coming from orbital and spin. Orbital and spin. Okay, so it is given as L and it is given as S. So again they will add or subtract to give you final value. Okay, so final MS. Final M. So one is the diamagnetism. Diamagnetism, right? The diamagnetism is like the inherent property of a magnetic material. You will find it in any type of magnetic material. Even if you take ferromagnetic material, you will find diamagnetic nature there. Okay, so it's just there in any type of moments. And if my spins, now more dominating is the spin. In orbital and spin magnetic moment, the more dominating is mostly taken as the spin magnetic moment. Okay. So yeah, in spin magnetic moment, if spins do not interact, so one thing I have. Now, if my spins do not interact, then I have paramagnetic. You have paramagnetic material, and if my spins interact, then I have ferro, antiferro, and ferric. Because spins are interacting. And why spins will interact? Because of exchange interaction. Now please bear with me, because exchange interaction is not a physically explainable term, because it is pure quantum mechanical term. So there is no like physical explanation. People have said it is a combination of electrostatic interaction and symmetrization postulate. See, it still doesn't make any sense. If you try to understand, it is a combination of electrostatic interaction. Okay, that is one term. Okay, we could understand electrostatic interaction is between a nucleus or the spins, between electrons and electrons, or electrons and nucleus. So that thing you can understand. Then what is a symmetrization postulate? A symmetrization postulate is nothing but so for example, if you have a wave function, and if I apply parity operator to to that wave function, then it will give you a minus value. For fermions, and for bosons it will give plus value. That's it. That's what we call symmetry, and that is where the symmetry postulate will come from. Okay? So if I apply parity or time operator to any wave function, then if I get a minus, that is called as for fermions, and it will get plus for bosons. And luckily, unluckily, our electrons belongs to fermions group. Okay, so whenever you try to apply a parity operator to any wave function of an electron, that parity operator will omit a negative sign. Okay, so please keep that in mind. Now, if my spins are interacting, ferro, antiferro, ferric, right? And if we are talking about molecular orbitals, where I have overlapping of atomic orbitals, then I will be dealing with molecular orbital theory. Okay, so yeah, in molecular orbital theory we mostly consider atomic orbitals. So this is different compared to these guys. Now moving on to, let's talk about the paramagnetic materials. Now their spins, we assume their spins are not interacting with each other. Just as ideal gas. In ideal gas, we assume there is no interaction between the gaseous species or gas particles, right? That's how you get PV equals to nRT. If you assume there is an interaction, then you will have some another term here, right? And if I have considered volume, then there is another term. These spins are not interacting with each other. Okay, so this is that. Now, how do I find the relation? So whenever we try about magnetic moment, so if I have a spin which has some magnetic moment mu b, and if I apply some magnetic field, then this mu b and h will interact, and that will create some energy, and that energy is given as mu b dot b. Okay, so mu b dot b. That's it. And you know mu b dot b will be mu b. If my spin is up, then it will be positive, and if my spin is down, so for example, if my spin is up and my b is in this direction, then my cos theta will be 0, that is 1, and if my mu b is down and b is up, then my cos theta will be 180, and that is equals to -1. for this guy, E equals to minus mu B B, because the electrons have negative sign, so that's why I was taking minus. And for this guy, it will be positive mu B B. Okay. Now if I want to try find out what is the magnetization for the whole material, right? Then let's say I have n number of upward spins, n number of downward spins. I'll write it like this, up and down. Then how do we calculate that? Then the magnetization will be number of spins by unit volume. This is my magnetization. No, that is not my magnetization. Magnetization will be magnetic moment of up spins minus magnetic moment of down spins. If they are perfectly equal, then magnetization will be 0, because if I have up, then there will be another one down. Then magnetization will cancel out. These spins will cancel out. The magnetization will be 0. Right. So for magnetization to be a real value, someone should be greater than someone. Right? Now how do I write it? How do I write number of up spins? And that is given as total number of spins times exponential minus energy of up spins upon Boltzmann KBT. And this is divided by the partition function. And what is the partition function? Partition function will be given as exponential minus E up spins upon KBT plus exponential minus energy of down spins upon KBT. And I know energy of up spins will be mu B B or minus mu. You can take anything, depends upon sign. And down will be plus mu B B. Now if I substitute them here, this will be exponential. I already have minus, so they will be mu B T plus exponential minus mu B upon KBT. Okay, now how does they look like? Exponential of x plus exponential of minus x will be equals to cos hyperbolic function hx cos x. People call it hx or cos x or anything. So then z will be equals to 2 hyperbolic of hyperbolic cos function mu b b upon kbt. Okay, so now if I write n up spins or down spins, which is equals to exponential, there is also n exponential, or I will write n at last, okay, that will be more good to write exponential. So if I am saying up, then there will be a minus. If I am saying down, then there will be a plus. Mu b b kbt on 2 cos h mu b b. See, I am not writing for n down. It's the best way of writing if you have two similar type of equations and there is only a sign difference, then you can just represent one by one equation, another equation by comma, and that sign here. If I have up, then there will be minus. If I have down, then there will be plus. That's it. Then what will be my magnetization? My magnetization will be n. So there is also n. Okay. Total number of spins. I forgot to add. Total number of spins upon my volume times mu b n up minus mu b n down. And if I substitute these guys here, m will be equals to n mu b upon v n exponential minus mu v upon kbt minus exponential mu v kt 2 wash h mu v upon kt. Okay, so then this will turn out to be n mu b upon volume, and this guy will be equals to sine. Right, this is equals to sine term. Okay, so then this sine term will be equals to 2 sine h mu b 2 cos h mu b 2 will cancel. There will be minus because of this guy, this minus, right, the sign minus. Then the magnetization, this is not mu, this is m. Magnetization will be equals to minus n mu b upon v tan h upon mu. Right, so if I say my temperature is high, let's say if T is high, then KBT is more dominant term. KBT is greater than mu b b, because my temperature is altering my spins. That means that is my high temperature. Okay, so if I am talking about high temperature regime, so my temperature is like my vibrations are altering my spins, this magnetic moment. Then what happened? Then my mu b b upon kbt is less than 1. If x is less than 1, then tan hx will be what? X. Then my magnetization will be equals to minus n mu b upon v times mu b b upon k minus n by v kbt times mu v square times. So what is my n by v? Total number of spins per unit volume, that is called density of spins. Density of spins. That means which is n, small m. Then write as small m. Then m will be n mu v square b times kbt. we are very close. Okay, so and we know magnetic flux intensity, magnetic flux density will be equals to mu naught times H plus M. Right, we know this relation very well. Now, if my material is linear, what do my material is linear? If my material is linear, then my magnetization is proportional to H, and this is called susceptibility. This is called magnetic field strength. Okay, so this is my one relation. Then B will be equals to mu naught H plus susceptibility of H. Now, if we know if our material is a paramagnetic material, our susceptibility will be less than 1. So B will be simply equals to mu naught H. Right? And H will be equals to B by mu naught. Then coming to M will be equals to N mu B square upon B divided by KBT. Right, so if I write this relation here, so I insert this guy here, then magnetization will be susceptibility times B by mu naught. So M will be equals to N mu B square upon KBT times B. And if I want that relation, then if I can multiply this mu naught on both sides, so this thing is equation 3, equation 2 looks same, then my susceptibility is equals to mu naught times the spin density, the magnetic moment density, the spin's density times magnetic moment of each spin square divided by KBT. And that means susceptibility is inversely proportional to the temperature. And if I remove the proportionality, then I will write it. This is inversely proportional to temperature. And if I remove this proportionality, I will remain with proportionality constant, and that is called as Curie's constant. And this is called Curie's law. Now you people know, right, how the Curie's law came. It is just a simple mathematics. I mean, not simple mathematics. There are many assumptions, such as my material is not in my material and spins are not interacting. That is the main assumption. Okay, so it will be a hyperbola. And if I put it like this, then it will be a straight line. That's it. That's all the paramagnetic materials. So if you want to know how, see, there is simple handiwork where you assume that if whenever say material is a paramagnetic material, you measure its susceptibility. And how do you measure its susceptibility? Susceptibility is nothing but the magnetization. If you measure magnetization versus the H, what does that mean? You have a magnet, you have some material, you apply magnetic field, you measure the magnetization. Okay, so you will get like values like this. you may get the result like this, or you can say not like this. It cannot linearly increase, right? So it can go like this, and it might. And if you remove the hedge, then it will come like this. This term, yes. Okay. So this is called MH curve. This is what we measure whenever we try to do this the magnetic testing. Okay. So it is done at constant temperature. And there is also another thing which is M versus T, which is not important for now. Okay. So the magnetization versus applied magnetic field will give you the curve. Now, if I do it like this, M by H, will give you a straight line. M by H will have a constant values, and that is given as susceptibility. So if my susceptibility is very low, then I can say my material is a paramagnetic material. Okay. So yeah, and there are soft magnetic materials, hard magnetic materials. So soft magnetic materials are nothing but it is easy to change their magnetization direction. See, this is a soft magnetic material because all I have to do is apply only this amount of energy, this amount of magnetic field, or only this amount of magnetic field. If I try to increase my magnetic field, this is my magnetization. Okay, so okay, if my H is 0, then I have my M value. This is my M value. Okay, so I will write it. I will explain it more clearly. Okay. Now, when H is 0, this is my magnetization. That means it is facing this side. Let's say it is facing upwards. All the signs are facing upwards. Now how to reverse this direction? And to reverse this direction, that means I have to make M as minus M. This is, let's say this is MR. Okay? This is positive MR. And I want to make it minus MR. Now how do I do that? To do that, I need to reverse the magnetic field. Right, the spins are in this direction, I have to reverse my magnetic field. Then if I increase my magnetic field, the magnetization will go down and it will 0. And this is called the coercivity, which is given as HC. Coercivity. And again I try to increase my HC, my magnetic field. My magnetization will increase and will go on saturation. If I again try to remove that magnetic field, I will come to minus MR. So that is the amount of magnetic field I need to, this amount of magnetic field I need to mitigate the magnetization to 0, to make it MS 0. So if my if my MH curve looks like this, so for example, it looks like this. Then what? I need to apply more amount of magnetic field to make M 0. Right, so HC1 is less than HC2. This is soft, this is hard. The name itself suggests that it is easy to demagnetize and it is hard to demagnetize. So that's all about for today's session. I hope I have explained the things that sir has missed. Okay, so yeah, he didn't derive the paramagnetic Curie's law, right? So how the Curie's law comes, how the susceptibility is changing with temperature. So that thing I have proved. And regarding the ferro, ferri, and antiferro, I'll just give a brief equations, not the whole explanation, because the whole explanation, if I want to give the whole explanation, then I need to take extra classes for sessions for solid state physics, right? So which is not possible, and also time taking. So I'll just give equations you can understand. You can just see those equations and understand, okay, how it is coming. Okay, there is no need to go through every point of it, right? And it is also not in the scope of this course. So thank you.